And welcome back to another video. This is about how I connect ESP8266 to WS2812B LEDs. Right, let's look at the software. This is very basic. So we've got a basic includes. Because we're using the ESP8266 FreeRTOS, then we need a few things to call in as our includes. Don't worry about the unsolved problem. That's a Eclipse issue and nothing to do with the software, and it will compile perfectly fine because it's compiling outside of the Eclipse environment. Right, we need to set up a pin. Pin 5 on the board I've shown you earlier has already got a connection to it, so we're going to use port 5 or pin 5. So basically we set that to our output. Don't really need it, you could just stick it here. It just looks it just makes it easier to understand. You know, we're going to set up a mask and we are going to put a 1 into it and shift it left by the port number, so it's 1 shifted left by 5. And then we come into the main and we need to set up a structure. Now there's the structure. Can't move. Can I move the mouse onto it? Yep. And it takes the pin bit, which is the masks of the GPIO pins you're going to use. Then it has the mode, which can be input, output. Then we move on to, do we enable pull-ups and pull-downs, or 1 is enabled, a 0 is disabled. And then there's the interrupt type, and that can be pull, interrupt on high, interrupt on low, interrupt on change, things like that. We're not going to have the interrupts, so we'll disable them. So here we go down, we're actually starting to fill that structure. So the interrupt type equals GPIO interrupt disabled. We want to put the pin as an output. We want to set pin 5 mask so that only pin 5 is used. We don't want pull-ups, we don't want the pull-downs. And then we pass that structure into the GPIO config, and that sets the port how we want it. Bit more complicated than just saying, in Arduino land, pin 5 output, but that's effectively what the Arduino will be doing in the background. Then we move down to the while loop, and while 1 means loop forever because it just takes true, so it just keeps going. We need a delay, and this is in the IDF. How do you create a delay? Forget the fact it can't be resolved. Again, that's a Eclipse IDE issue with indexing and things, and I've yet to find a way of fixing it. So effectively that's a millisecond, so times it by 1,000, you get a 1 second delay. This is how we set the output. So first of all, I'm going to set it to a 1, and then I'm going to set it to a 0. And what I'll do now is, up in this corner, I will show you what that does as a timing pulse to give you an idea of how this bit of code can't be used for an ESP8266 and a WS2812. Well, showing on the scope above, you can see that the DT, or the time of the pulse, is 364 nanoseconds. That's the best you're going to get using the chip at that speed of clock, which isn't fast enough to drive the LED properly. Just to make life easier, what we'll do is we'll just cut and paste in some extra commands or extra includes. we'll just bring this in, which again the Eclipse won't like, is they allow you to talk to the output pins in a slightly different way. So here we have GPIO reg right, and we have GPIO out W1TS, which is for set, and then the LED data, which is the pin number, and then we have the GPIO reg right W1TC, which is the clear, and so that will clear it. There's also, you have to define the LED output slightly different, so we'll add that in as well. So it's bit 5 this time, rather than a 5 being right left shift, 1 being left shifted by 5 to get the mask. This now is just bit 5. Highlight, copy them out, rid of them, and it should compile. Well, I'll pop up a shot of the scope, and you'll see now that the pulse length, the pulse width, sorry, is now down to 76 nanoseconds. Gives us a chance for those pesky little LEDs. All this with a simple change in the code. Well, if we look here, this is the data sheet for WS2812B. The timings for the low high, 400 nanoseconds or 0.4 microseconds. T low 850 nanoseconds. So we're looking at about twice the low time to the high time, approximately. And for 1, it's 800 high, 450 nanoseconds low. Again, it's about 2 to 1. If we go back to our code, bring in some defines, save me typing it out, I'm just going to copy and paste them in. So we have 0 high, 4, 0 low, 7. So why don't we make that an 8? So that's exactly like half the high time to the low time. And we'll do the opposite for the 1s. It will be on for twice as long as it is low, and then we'll look at the scope in a bit when we see what happens. Right, so the next bit is we want to generate a low signal. So basically it's 2 while loops counting down, setting the output high, and again setting the output low. So that sends 1 bit, that sends a 0. The 1 is effectively the same. We could probably merge them together and have one that does both, but I like to be able to just see that there are differences. So this one again is going to set the high bit for longer than it sets the clear bit or the low bit. And just to see how it works, we'll comment those 2 lines out as we don't want them, and we'll do a quick for loop to send it out. Right, let's compile that and send it to the chip, and we'll see what it does on the scope. Well, here you have it. You can see the scope. It's not exactly a fast cursor on this scope. It's not the best scope in the world, but it was relatively cheap. So if we look there, we were looking for a 400 nanosecond pulse. We got a 425 nanosecond pulse. Camera on control. If I move that over, we'll see that the low pulse is 865, so pretty close to what the spec wants. And of course, if we bring it in, you'll see there are 6 of them, which is 0 to 5. So that shows, or the 0 bit is working. Right, we'll modify the code, and we'll just say it so that it sends the 1, and we'll have a look at what 5 1s look like. So I'll flash that over. Right, here we can see the scope again, and we'll just check this is the sending a 1. we have a high pulse of 790 nanoseconds, not quite close to the 800 we want. And the low pulse, so a little bit long. So maybe if we can just go up, and the reason we got defines for them all is take that out. We could knock that one down to a 3, and that will knock the low down a little bit, but it's close and it's probably good enough. So we'll leave it at that for the moment and move on to the next stage of driving the LED. Now we have the data pulses correct. Right, now we're going to add a few more defines so we can move on to making the LEDs work. So let's clear a bit of space. First of all, don't like magic numbers. Magic numbers are numbers that appear in your code that are just numbers. They're hard to understand. So you put a 2 and you think, what's that 2 mean? Well, if you write number of LEDs and define it as 2, then every time you type the number of LEDs, you know that that's the number of LEDs. And the same with LED data size. That's not going to change. That's always 3 bytes or 3 chars. And the int mask, the initial for it, initialization of it will never change. It's always going to be the most significant bit that's been set. So then we're going to create a structure, and this is to describe the LED itself. So basically we're going to have a structure. We're going to call it the WS2812B, and it's going to contain a green, a red and a blue char. That is how we're going to describe the LED. Next, what we want to do to make our life a bit easier is we want to have like an array of them. So we're going to have another structure, and this time what we're going to have is we're going to have a structure called LED out, and it's going to be a union of an array of those structures and an array of unsigned 8-bit integers. And the array is going to be the number of LEDs times the data size. So if you change them up top, this will automatically update itself when you next compile it. And then the final bit is we need to place that information into memory, and we do that by creating a structure called LED, which is of type output. And what I'm going to show now is just a little idea. Here's the structure for WS2812B, and you can see it's made up of 3 integers called red, green and blue, and that's the structure down here. And then this structure gets called up in here in this LED out and the union, and you can see that it's created, say we're going to do 3, so number of LEDs is say 3. So whoops, there you can see 1, 2, 3 LEDs. There's the structure in them, so there's repeats 3 times. But then you get the LED array, and that's the number of LEDs, 3, times 3, which is 9. So you're going to get, just move it down slightly, an array of 9 charts. And because it's a union, those and those overlap. They occupy the same space in memory. They are just 2 ways of talking to that memory. So our structure LED out, we've got LED.LEDs 0.green is referencing that. But then you've got LED array 0 is also referencing that. And again here, LEDs 1 red is that point, but LED array 4 is also that point. The reason to do this is I can talk in my program of LEDs 1, 2, 3, 4, 5 so I know where they are, and all I'm concerned with is LEDs whether I'm setting it as a green, a red or a blue. But when it comes to sending the data out, I want to increment through that really easily, and I can do that with the array, because I don't really care what the array is looking at. All I want to do is start off at 0 and send each one of those out 8 bits at a time. So that's the sort of the plan, and that's what the kind of structure arrangement does. So back to that, that's our union, that's the final structure that's placed in memory. Then, just for our own example, we want to go down into our main application, and just before we do the loop, we want to just put some data in. So we'll make the first LED green and the second LED red. So we're just filling that array. And then down here, we really want to get rid of those because they're no longer doing anything, and bring in a new bit of code. And basically, we've got a loop that goes from 0 to the number of LEDs times LED data size minus 1, because obviously it starts at 0. And we iterate through that. And then here, each time we go through, we initialize the mask back to 0x80. So we're starting at the most significant bit. We bring in the next array item, the next 8 bits. And while the mask is true, it's not a 0, we AND the byte we're looking at with the mask. And if it's high, we send a 1. If it's low, we send a 0. Then we shift the mask 1 to the left and go around again. So that will send each 8 bits in that byte. When it gets to 0, when that 1 falls off the end, the while will become false. It will exit out and go through, bring in the next array item, go through again. And that's all it does. Pretty simple. So we'll compile that and we'll have a look on the scope. Right. Did anyone spot the silly mistake? Looks good on paper, but won't program. I love it when we make mistakes. And you've seen it, so I couldn't hide it. So away we go. Let's flash it again. Right, here we are looking at the scope, and just looking at here, the transition between it's been sending lows, so short high, long low, and it's gone into sending a 1, where it's now sending a longer high and a shorter low. And if I bring the camera back, if I bring the camera down, there's the board, there's LEDs. Camera doesn't really show them up very good. If we bit better, I suppose. Green and red. So there you have it. How to drive some LEDs. If you only want 1 or 2, you only want to say, like, if you only have 1 and you want to go it's green or it's red or it's, as a status, you don't want fast LED and all that stuff. So how about just having some simple code? You can expand it to as many LEDs as you like, as long as you've got enough memory for the array. But then if you're going to do lots of LEDs, fast LED gives you a lot more things you can do with it. But if you just want a single LED or 5, and you don't want to have the overheads of loading fast LED library in, because all you're going to do is turn them off, dim them, or things like that, nothing too complicated, then that's the way I do it. Thanks for watching. It's been a long one. Hope you liked it. And, hit the subscribe button, click the bell, and I'll catch you on the next one.